All right, guys, brand new stuff today. Estimating a population proportion. My advice is take quite a bit of notes. This thing has a bunch of slides too, and I'm going to try to go as quickly as I can. Stop as much as you need to. Really important stuff. Don't know much to say besides that, so we're going to hit it right here, but please take some great notes. All right, a review from where we've been. Chapters 2 and 3, we used descriptive statistics where we found stuff like mean, standard deviation, things like that. In chapter 6, which is what we just finished, even though we don't talk about what chapter numbers we're on, we did critical values. You got to remember what those were. It was Z with a little alpha. And what that's a Z-score with an area of alpha to the right, always to the right. We looked at alpha that, the critical value, we just looked it up in the table or on a calculator and got 1.96. That means it has 0.025. If you find that Z-score 1.96 has that much area to the right. So we're going to put all that stuff together and do some stuff with it. Preview what's coming. This chapter is the beginning of inferential statistics. We're going to start inferring things, not just finding numbers, but inferring things from that. Two major activities. One, we're going to use sample data to estimate population parameters. And number two, we're going to test hypotheses or claims made about the population. We're going to introduce methods for estimating values of these parameters using proportions, means, standard deviation, variances. We also got to figure out how big sample sizes must be in order to estimate those. That's where we're heading. All right. Key concept. In this section, we present methods for using a sample proportion, or only proportions today, to estimate the variable population proportion. Big thing right here. The sample proportion is the best point estimate, or the best targets the population proportion. We can use a sample proportion to construct a confidence interval. That's what today's lesson is mainly about, to estimate the true value of a population proportion. We should know how to interpret such confidence intervals. That's a big thing for today. Tomorrow we're going to look at this. How big is the sample size necessary to make a good estimate? How big does the sample size need to be? All right, a point estimate, that was the word on the last slide, is a single value, or point, used to approximate a population parameter. So just a point, in this case, we're going to be the sample proportion is going to be our point estimate to estimate the population proportion. Sample proportion is p hat, don't forget that, is the best point estimate of the population proportion p. A quick example, the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. The best point estimate of the population is the sample proportion, which is p hat. P hat is 0.85. So we would say, okay, that means that's the best guess of our population proportion. A confidence interval, or interval estimate, we're going to do a lot of confidence intervals, is a range or an interval of values used to estimate the true value of the population parameter. Now, when we find a sample proportion or statistic from our sample, it's not going to be exactly, probably, sometimes it could be, but probably not exactly what the population parameter is, but we can get an interval and say, okay, the population parameter has got to be somewhere in this interval, and we're going to call that interval the confidence interval, or a confidence interval, or CI. Confidence level, we're going to have different levels of confidence, and all we're going to do to get that level is we're going to do 1 minus alpha. Don't forget you saw alpha with the z-score, like z alpha, the critical value, often as a percent, that the confidence interval actually does contain the population parameter. So we're going to say, well, I'm 90% confident that the parameter's in here. I'm 95% confident that the parameter's in here. I'm 99% confident. And if those are the case, alpha corresponds to those. Alpha 0.10 goes with 90, 0.05 goes with 95, 0.01 goes with 99%. Okay, so we're going to describe it using percentages, but we're going to have to use these alphas to find our intervals. Okay, interpreting them. Must be careful how to interpret confidence intervals. There's a correct interpretation and many different and creative incorrect ones. Let's say that's our confidence interval with the Twitter thing a minute ago. So we know the population parameter is somewhere between 82.8% and 87.2%. So we could say this, okay, if we use a 95% confident interval, we're 95% confident that the interval shown there actually does contain the true value of the population proportion. That means that if we were to take many different samples of the size 1007, which is how many we did a minute ago, and construct corresponding confidence intervals, 95% of them would actually contain the value of the population proportions. A couple would not, all right, but 95% of them would. And again, it's the same thing. Be careful here. Confidence intervals can be used informally to compare different data sets, but if you overlap confidence intervals, overlapping them should not be used for making formal and final conclusions. So be careful, and we'll talk about more about that a little bit later. A confidence interval can be used to test some claim about a proportion, P, which is what we're going to be doing as we go on. Critical values, we did these already. A standard z-score can be used to distinguish between, listen to this very carefully, distinguish between sample stats that are likely to occur and those that are unlikely to occur. We've talked about those words before. Such a z-score is called a critical value. Critical values are based on the following observations. Number one, under certain conditions, the sampling distribution of sample proportions can be approximated by normal distribution. Imagine that, we've never done that before. Number two, a z-score associated with the sample proportion has probability of alpha divided by 2 of falling in the right tail. We'll talk about what that means right here on the slide. Right tail means over here. The z-score separating the right tail region is commonly referred to as z, or the critical value of theta divided by 2, and is referred to as a critical value because it is on the borderline separating z-scores from sample proportions that are likely to occur and those that are unlikely. In this case, the green area right here, likely, the red area, unlikely to occur. Big, big deal right there. 95% confidence level, which we're going to do is we're going to take our alpha, if it's 95%, our alpha would be 0.05, but to do our tails, you do alpha divided by 2. So if you do 0.05 divided by 2, you get 0.025, and those would be our critical values. Right there's our critical value. Look up the table or punch in your calculator, you get 1.96. That's the critical value for a 95% confidence level. Now, that's the critical value every time you do a 95% confidence level. So if you memorize that right there, you can just use it over and over again if it's a 95% confidence level. These are the common values, and here again, there's the 95%, 1.96. If you use a 90%, there's your alpha. It's always going to be 1.645. If you use 99%, there's your alpha. It's always going to be 2.575 or 2.58. When data from a simple random sample are used, and that's a big deal. We can't do any of this if we don't get data from an SRS or simple random sample. Are used to estimate a population proportion, the margin of error, denoted by big E, capital E, the maximum likely difference with this probability, such as 95%, between the observed P and the true value P, is the margin of error. Now, when you take a sample and find your little P hat, it's not going to be exactly big P probably because you're not going to hit the population proportion exactly in a sample. So there's a little bit of an error. And we call that the margin of error, or we use the big E for that. And that's where our confidence interval is going to come from. Okay, margin of error. Here's how we're going to find the margin of error, or big E. First of all, it's also called the maximum error of the estimate. There is an error to an estimate when you're estimating the population proportion from the sample proportion. All you do is this right here. You take the critical value, that's Z alpha divided by 2, that's the critical value, and square root of P hat times Q hat over N. And what that is, that's the standard deviation of sample proportions. That's how you find the standard deviation of a sample proportion. So that's all it is, the critical value times the standard deviation of the sample proportions. All right, confidence interval for estimating population proportion. This is just the symbols. Make sure you know what they mean. This is a quick review. P without the hat is the population proportion. P hat is the sample proportion, what you found in your sample. N is how many sample values are there. Big E is the margin of error, or, well, just margin of error. And that's our critical value, Z with alpha over 2, separating the likely and the unlikely in the right tail of the standard normal distribution. Confidence interval for estimating is how you do it. Number one, the sample must be simple random. Just talked about that. Number two, the conditions for binomial must be satisfied, meaning there's a fixed number of trials, they're independent, there are 2 categories of outcomes, and the probabilities remain constant for each trial. They're independent. There are at least 5 successes and 5 failures in order to do this. And here's how we find it. To find our confidence interval, we're going to say this. We're going to say, okay, P, our population proportion, is in between these 2 values. Our P hat minus our margin of error, and our P hat plus the margin of error, which is really this right here, P hat plus or minus margin of error, where our margin of error, or maximum margin of error, is a critical value times our standard deviation, or critical value times the square root of p hat q hat over n. Round off rule. We're going to go 3 sig digs. Notice it doesn't say sig figs. Sorry. 3 significant digits, 3 sig figs. Round it every time, our p to 3 sig digs. So if you notice a few minutes ago in that example, I had three decimal places. Quick example. In the chapter problem, the same one we read a minute ago, we noted that a Pew Research Center poll of 1,007, that's our N, 1,007 randomly selected adults showed that 85% know what Twitter is. The sample results are N equals, there's our sample size, there's our p hat. Part A, find the margin of error that corresponds to a 95% confidence level. Find the 95% confidence interval of the population proportion. Based on these results, can we conclude that more than 75% of adults know what Twitter is? And part D, assuming you're a newspaper reporter, write a brief statement that accurately describes the results and includes all the relevant information. Here we go. First of all, requirement. It did come from a simple random sample. That's fine. There's a fixed number of trials. There's 1,007. They're independent. When you ask one person, their answer doesn't affect the next. There are 2 outcomes. You either know what Twitter is or you don't. Probability every time remains constant. It's 0.85. No number of successes and failures are both at least 5, obviously, because 85% said that. So 85% of 1,007 is bigger than 5, and so is 15% of 1,007. Okay, we've got to find the margin of error first. So I found my critical value. First of all, critical value at 95% was 1.96. There's my p hat, there's my q hat, and there's my n. Just punched it all in the calculator. There we go, 0.022. All right, part B, find the 95% confidence interval. So all I'm going to do is I'm going to take my p hat and subtract what I just found for my E, take my p hat, add what I put for my to p hat, and then put p in between. So I did that right here, subtract it, add it. There's my confidence interval. So 3 sig digs, 0.828 and 0.872. So, well, let's go to part C. Part C, here's what you can conclude. Based on the confidence interval obtained in part B, it does appear that more than 75% know what Twitter is because the limits of this are likely to contain, or like, I'm 95% sure the population mean is the population proportion is in between those two. And that's bigger than 0.75. That's why I'm very confident that, more than 75% of adults do know what Twitter is. And part D, if you're a reporter, how would you say this? You would say 85% of U.S. adults know what Twitter is. That percentage is based on the Pew Research Center poll of 1,007 randomly selected adults. Notice all the information in there. In theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points in either direction from the percentage. So if you do tons and tons of polls, 95% of them will fall within 2.2 percentage points either way of 85%. Based on what our margin of error was. Hope this is making some good sense to you. Okay, analyzing polls. When you look at polls, number 1, the sample should be a simple random sample, always that, not an inappropriate one like a voluntary response. Number 2, the confidence level should be provided. These should tell you how confident you are, 95% confident. Some polls do and some don't. The sample size should be provided, usually not. Number 4, except for rare cases, the quality of the poll, this is big. The quality of the poll results depends on the sampling method and the size, not the size of the population. That's not usually a factor, which is kind of weird. Sample size matters and the sampling method matters, but not necessarily how big the population is. Last slide finally. Never follow the common misconception that poll results are unreliable if the sample size is a small percentage of population. If you're going to take a sample of U.S. citizens, your sample size is going to be a small percentage. Here's the deal. The population size is not usually a factor in determining the reliability of a poll. It's usually how you did it. It's an SRS and how big the sample size was, not how big the population is. All right, so that's a lot of stuff. Sorry for the length of the video, all the slides. Hope you got some good notes. Make sure you answer the question. We'll work on this stuff tomorrow. And make sure you got your calculator with you. Much better than StatCrunch tomorrow for sure. See you then.